Okay, we're now going to talk about the change of variables called rotation. Notice that we're in 2D, and so whenever you go to higher dimensions, you always have more complexity. And so in 1D, there was just u subs. But in 2D, really there's all kinds of things you can do. And so we did rescalings before, but now we're going to talk about rotations. And the idea of rotation is just if you have some asymmetric region, then after this transformation, it'll be the same region, but it'll just be rotated. And it could possibly be scaled as well. So it might get bigger under this. I think the essential feature is that just this rotation part. So let's just think about an example integral. So let's take the integral of e to the x plus y dA. Notice that there's this x plus y, so the more complicated an integral seems, the more likely there's going to be some trick involved, right? So the region R will be x plus y absolute values less than or equal to 1. Okay, so that's weird, right? I think the important thing to start off with is to draw the region. And so what you do is you partition greater than 0 and less than 0. So there are several cases, right? So x greater than 0, y greater than 0. And let's draw them on the xy plane. And really what's going on is x is also less than 1, y is also less than 1. So I'm just going to put a box, and I got this less than 1 just from this inequality, because surely this means x is less than 1 and y is less than 1 as well, because you can just draw, because this y thing is positive. So here's the box of size 1. So in the case A, really you can replace absolute value of x with x, and you can replace absolute value of y with y. So our inequality becomes x plus y less than or equal to 1, otherwise known as y less than or equal to 1 minus x. So we're going to draw the line 1 minus x, and I'm just going to put an arrow downwards to indicate the region. Okay, so that wasn't bad. And we could just label this as x plus y equals 1. And I'm going to keep it as x plus y, and we'll see why. Because notice already there's a parallel with the integrand, x plus y and x plus y. This is not an accident. And as we saw with rescaling, it'll turn out that these things will be, the relationship between these things is crucial. So let's go to case B. I'm going to also label this A. Now let's do case B, where x is less than 0, and really it's greater than negative 1 by symmetry, and y is still greater than 0. Okay, so that means absolute value of x goes to negative x, right? Because x is negative, so we need to negativize it. And then y is also just positive. Okay, so that means our inequality becomes negative x plus y is less than or equal to 1, otherwise known as y less than or equal to 1 plus x. Okay, so 1 plus x is shifted upwards, so I'm going to draw the second line as follows inside the box. Okay, now let's do C. C will look similar. So it'll just be x less than 0, y less than 0. I'm going to third. I've been moving around the quadrants. So this is the first quadrant, this is the second quadrant, this is the third quadrant. Okay, so now that means absolute value goes to the negative for both cases. So really what we have is negative x minus y less than or equal to 1. And if I just move that y to the other side and move the 1 to the other side, really what this is negative x minus 1 is less than or equal to y. So negative x is shifted downwards. So I'm going to draw the line. Again, you can see really what we have is a diamond. I'm going to label this B as well. And this, let me just label this really quickly, minus x plus y equals 1. And so I'm going to, the last thing I'm going to do is factor, because notice this is minus x plus y less than or equal to 1. So notice it's opposite in sign to the other one. Really what this is x plus y equals negative 1. And that's important because now we'll eventually be treating x plus y as our u. And so really, the top side A corresponds to u equals 1, and side C corresponds to u equals negative 1. Okay, but we're getting ahead of ourselves. Let's go to part D. X greater than 0 in the fourth quadrant, and y less than 0. So our inequality becomes x minus y less than or equal to 1. Okay, and you can see what the line should be, right? It's just going to finish the diamond off. And this is minus x plus y equals 1, otherwise known as minus x plus y equals negative 1. Right, so it's the same function as part B, but now it's just the only thing that's different is the negative 1. Right? So as we go from B to D, the plus 1 becomes a negative 1. And as we go from A to C, that plus 1 becomes a negative 1. Okay. So now that we've figured this out, what you'll do is you'll make a change of variables, and you'll use those functions defining the boundaries. So change of variables, and use for u and v the xy functions defining the edges or boundaries, whatever. So that means, so what I mean by this is x plus y and x, or minus x plus y. You could use x minus y. I don't think it matters, but you might get a sign issue. Okay, so what I'm saying now is let u equals x plus y, and v equals minus x plus y. Okay, so now redraw the diagram in UV space. So the old diagram in XY space was just this diamond, and it was x plus y equals 1 for this edge. It was minus x plus y equals 1 for that edge. It was x plus y equals negative 1 for that edge, and it was minus x plus y equals negative 1 for this edge. Okay? So if we plug in now u's, I'm going to write the u's in red. This is u, this is v, this is u, this is v. So really that's u equals 1. So now I'm going to redraw this in UV space. So u equals 1. I'm going to call this A, B, C, just to clarify how this is transforming. Really, at 1 we have u equals 1. There's also a u equals negative 1. And then there's also a uv equals 1 and negative 1. So the u equals 1 side, that's A. The v equals 1 side, that is B. The u equals negative 1 side, that is C. And the v equals negative 1, that is D. Okay? So this is our region. Now that was how it transformed. Really, I should have put the minus on the y, but I don't think it matters. Yeah, so this is the new region, and so this is a better region. I would say it's the simplest possible region. Because now it's just rectangular. Okay? So integrals are much better along such regions. So now the final step, all we need to do, if this was our r, this is our r bar. Right? So we've figured out that our integral in r can be rewritten as integral over r bar. So our final step is to find the Jacobian. Okay. So to find the Jacobian, it's more complicated than in rescaling. So there's I would say there's a formula that you need to that you need to know for these types of more complicated transformations. Let me introduce it like this. What we want to do is rephrase dx dy in terms of du dv. So it'll be this Jacobian times this, and this thing is written, of course, like xy divided by uv. So the thing is, so what is this formula? It turns out this is equal to the determinant of dx, du, dy, dv. I would always do the diagonals first, because they are the way you want it to be. But now the off diagonals, what they will be is dy du, you just change. You switch it. And then you switch, and then you do another switch. Dx dv. Right? So all four possible combinations are listed, and the good ones are listed on the diagonals, so to speak. Okay? So it's the determinant of all these partial derivatives. But here's a tip for notation. To save yourself some time. One very common abbreviation for partial derivatives is just to do x subscript u. You could do y subscript u. You could do x subscript v, and then finally y subscript v. Notice that now we only have two letters instead of all of these d's and that fraction bar. So I kind of like this notation, but you can use whatever you want as long as I know what you mean. Okay? So you just need to take that determinant, and remember the determinant is product of the diagonals. xu yv minus xv yu. Okay? And so in this case, well, actually in this case we're given u and v in terms of x and y. So what I would do is just flip the Jacobian. So d x y divided by duv is 1 over exactly what you want it to be. duv divided by dxy. Right? So it's 1 over this other determinant. So ux, vy, let's see, vx, and uy. Okay. So let's evaluate this. So ux, remember I'm just going to circle the transformation, and really now we just have 1s and negative 1s. So it's 1 divided by 1, negative 1, 1, and 1. Okay, so the determinant is pretty easy. It's just 1 times 1 minus negative 1 times 1, so it's 1 over 2, 1/2. Okay? So that is the Jacobian. And that's the thing you stick in front of that du dv. I want to mention, just to remember what this, notice that dxy, duv, du dv, the du and the dv cancel formally. That's to help you remember which one goes on top. Right, because this is just a way of writing dx dy, so of course the du and the dv have to cancel. That's just a heuristic to help you remember what's going on. So now let's just do the integral. So our integral over that diamond of e to the x plus y dx dy, now it's equal to the integral over the square of, well, our transformation, let me just write it down again. X plus y equals u minus x plus y equals v. So it's e to the u. And cy, now it's better because notice that there's no v dependence, so that's pretty good. And then our Jacobian was 1/2, so now we have a 1/2 times du dv. And the square that's in question, it's just the best possible square. It's just from 1 and -1. So you could just do -1 to 1, -1 to 1, and whichever order you like. Let's say v and u. Okay? So now this integral is easy. Okay? So you can see that the rotation made this kind of complicated looking integral a lot better, actually. So, and I would say rotation is the second most important change of variables. There's many instances where you have an integral of, for example, e to the x squared minus y squared. If you have some integral of something complicated, what a rotation will do for you is, like in this example, it would turn this into e to the uv, and it turns out this is a lot simpler to think about. It's sort of you can see already from this example that rotation places it in a much simpler form, and I'm just saying that this shows up a lot in many complicated integrals. So I hope this was a useful trick. Thanks for watching.